Hello everyone. So today we're going to continue on 6.4. So our last video we talked about Lagrange multiplier method, and that allow us to identify critical points along the boundary. And we also already learned how to find critical point along the interior. So now the next thing I want to talk about is the following. What if we have a function that we want to find the max and the minimum of, but it doesn't have a close domain? And when that happens, we don't actually have a boundary, because remember, if you don't have a closed domain, that would mean that the domain must be open, therefore only have an interior and doesn't have any boundary. So therefore, we on the good thing is that would mean that we don't need to use Lagrange multiplier method. We can just simply find interior critical points. But the bad thing is that we will not be able to use extreme value theorem to determine whether we have a maximum or minimum. So we cannot use a table. So what we need is actually to determine whether we have a relative max or relative minimum. And that's what we're going to talk about in today's video, as well as mostly tomorrow's video. So to start from that, we go do a little quick review first. From BC calculus, you have learned that you can determine whether a critical point is a relative maximum or relative minimum, or actually could be neither, using something called the second derivative test. So when you first learn about it in BC calculus, you probably often wonder, like, why do we have to learn second derivative test? It seems kind of pointless because you already know first derivative test, and you already need to use the first derivative to find critical point to begin with. So what's the purpose of using second derivative test? Well, the idea here is that second derivative is actually not that useful in single variable calculus, but it's actually extremely important in multivariable calculus for a reason that we'll talk about in a little bit. So before we move on, let's do a quick review of what second derivative test is. Okay, so second derivative test. The reason why I want to do that, because we're going to develop something similar to second derivative test, but for multivariable calculus. And we're going to use that to determine where the critical point is a relative max or relative mean or neither. So let's say we have a second derivative test. So let's say, here we go. Let's say we have a function f that maps from R to R. And let's say this function be twice differentiable. So therefore, its first and second derivative must both exist. And we also going to have a critical point at some value x sub 0. So what does that mean when I say critical point x sub 0? Meaning imply that f prime at x sub 0 is equal to 0. So remember, critical point in this case, someone might think, well, can f prime of x sub 0 does not exist? Not at all. The reason why, because we want this function to be twice differentiable. So therefore, it would not have anywhere where the function have an undefined derivative. So the second derivative test basically states the following, 3 scenarios. So this might be slightly different than the second derivative test that you remember from BC calculus. If f double prime at x sub 0 is greater than 0, then f has a relative minimum at x sub 0. The reason why that is the case, because f double prime at x sub 0 is greater than 0, indicate that at x sub 0, the function is concave up. And if you have a critical point where the graph is concave up, then you must have a turning point where it goes from decreasing to increasing. That's the only way to fit a concave up curve. So therefore, we have a relative minimum. On the flip side, if f double prime of x sub 0 is less than 0, then therefore imply that we have a concave down curve. A concave down curve would indicate that a turning point at a concave down curve must be a relative maximum at x sub 0. So important to understand is that you must first identify that you have a potential turning point. That's the reason why x sub 0 must be a critical point first. And then you examine the concavity, and that's how you know what happened to whether you have a relative max or relative min. Now, a third scenario, which some of you probably remember from BC calculus, is the inconclusive scenario. But here I'm going to do a little bit more in depth and say, if f double prime of x sub 0 is equal to 0, that usually is the inconclusive state. But I'm going to identify one extra thing, and changes its sign at x sub 0. Then f has neither a relative max, max, nor a relative mean. Relative. As a matter of fact, in this case, you should know exactly what happened. F has an inflection point. Inflection point. At x sub 0. So when you have an inflection point, it cannot have a relative max and relative min. Okay? And it only happens when you have f double prime equal to 0 and it changes sign. What if it doesn't change sign? If it doesn't change sign, then I would say then you can say it's inconclusive. But you can probably also look at what happened before and after and realize that it might be positive or might be negative, and therefore revert to case 1 or case 2. So that's our second derivative test. So some of you probably remember this from BC calculus. If not, hopefully this kind of jogged your memory a little bit. So now what we're going to try to do is try to apply this to a several variable function. But there's a problem. Okay, the problem is the following. Why do we want to do this? So now what we're going to try to do, now we're going to take this idea of a second derivative test and applied it to real value functions of several variables. So here comes the big question of why do we do this? Why don't we try to apply the idea of a first derivative test and apply to real value function instead of second derivative test? Well, the problem is the following. Let's say, for instance, let's say given a function f that maps from R2 to R. So very basic function. So here f represents a two-dimensional surface, or if you want to just say surface, it would be fine, in R3. Now imagine the following. Imagine that we have a critical point. Let's say, let x sub 0 be a critical point for function f. Now here comes the big problem. So to use a first derivative test, we must be able to identify what go before the critical point and what go after the critical point and see there's a change in the first derivative. That worked when you have a single variable function because your value, your x value, your input is on a number line. Therefore, there's a definitive before and after. The problem with a function like this one, where the domain is the xy planes, any point on this xy plane x sub 0 would have infinite direction that can go toward this one point. And therefore, there's no definitive before and after to really speak of. And that's one of the reasons why the first derivative doesn't work, because in two-dimensional, there's no longer a way to order every point on the two-dimensional space anymore. Unlike one-dimensional space, every number has a definitive order from smallest to largest or larger to smallest. We can no longer do that in two-dimensional space. And therefore, first derivative is really no-go for us. Now, second derivative tests, on the other hand, are a little bit better, and we'll talk about how to bypass that problem. Second derivative tests also have the same issue. But before we get to that, let's talk about what does the second derivative test for multivariable calculus look like first. And then that way we can then explain how that works. So, definition. We do this thing called second derivative criterion. Basically define some criterion that would allow us to determine whether a function have a relative max and relative min. And the concept is similar to the second derivative test that we just defined. So show you. Let's say let f map from R and to R. And let's say this function be twice differentiable. Now, I know some of you probably thinking that way. Does that mean that we can do the gradient of the gradient? No. The word twice differentiable in this case meaning it all is second order partial derivative exists. Okay? So it doesn't mean they have two gradient, because remember, gradient does not allow us to do higher order gradient vector. But partial derivative does. So therefore, I say twice differentiable, meaning that has first and second order partial derivative. And have a critical points at vector x sub 0. So once again, what does that mean? That implies that gradient of f at vector x sub 0 is equal to a 0 vector. So notice that this is almost exactly the same as what I just wrote for the second derivative test, except kind of make it into multivariable calculus. So here come the three cases that we have to consider. Number one, if the partial directional derivative of f in the direction of u, the second partial derivative in the direction of u, at the point vector x sub 0 is greater than 0 for all unit vector u, then f has a relative minimum at x sub 0. So let's try to understand what this is saying first. So this basically tells me that if I take any direction u going toward or out of x sub 0, and I take the second directional derivative in that direction, that second derivative is greater than 0 for every single direction that I choose, then we have a relative minimum at x sub 0. Now, why is that the case? Well, the idea is that if you think about this picture that I drew, notice that at any one point, there are actually infinite number of lines that can go through that point. So this statement basically states that if every one of these lines, when it go through the point, it will result in the surface forming a upside down, a concave up curve. If every direction form a concave up curve, then the surface must form a shape that look like a paraboloid that we learned before. And therefore, we have a point on the bottom of the surface, and therefore result in a relative minimum. So essentially, basically meaning that this describes a scenario where you have a parabola, a right side up parabola, a concave up curve, spinning around some kind of rotation to form a surface. And therefore, you have a point on the middle. 2. If the second directional derivative in the direction of u at x sub 0 is less than 0 for all units vector u. Then the function f has a relative maximum at x of 0. So this describes the exact opposite scenario. Imagine every point that go through x of 0, every line that go through the point x of 0, if they all result in a concave down curve on the surface of the function f, then the function f must have a kind of a highest point on the top, like an upside down parabola spinning around, and therefore result in a relative maximum. So in other words, this basically forms this picture, where you have a relative minimum at the bottom, while case 2 would basically form an upside down graph where you have a relative maximum at the top. But that must be true when every curve that goes through these points are concave up or concave down for every direction. So therefore, it has to be for all unit vector u. So what happens if not all of them are satisfy this condition? Well, that would be case 3. Case 3. If d square f over d vector u square at x of 0 is sometimes is positive for some unit vector u and negative for other then f has neither a relative maximum nor a relative minimum. Notice this also mirror the second derivative test that I state, where it kind of like changes sign in some cases and for u and then change to a negative for some other u. And in this scenario, in this case, f, instead of having a inflection point like in the single variable case, f has a saddle point. At x of 0. So the saddle point basically kind of like the inflection point in the single variable calculus, where it kind of have a concavity change. Now, of course, there are two major issues with relating to how to apply this rule. So let's talk about them. So what are the two issues with it? Number one, what is this thing? I mean, we have never defined what this is to begin with. So what is it actually? Oh, I forgot a square. Okay. So that's the first problem. And two, how to show whatever we need to be true how to show which case it is if there are infinitely many vector u. So those are the two issues that we have when we try to apply this theorem. So number one is obviously we have to define what is d squared f over d vector u squared, and two is that there are infinitely many vector u, and we have to prove that for all vector u it satisfies a certain condition. So obviously we cannot go through each direction vector u one by one because there are infinitely many of them. So we're going to have to figure some way out to kind of know how to show that is true. So let's tackle these two issues one at a time. Let's start with the first one. So what is actually d squared f over d vector u squared? So d squared f over d vector u squared is called the second directional derivative of f in the direction u. So as the name suggests, it is a second order directional derivative. So therefore, it's basically derived from the first order directional derivative. So let's go ahead and do that. So therefore, imply that d squared f over d vector u squared is basically taking the directional derivative in the direction of u of the directional derivative of f in the direction of u. And this scenario, df over d vector u is basically the directional derivative of f in the direction of u. So basically, you're taking the directional derivative in the direction of u twice. Now, but of course, that doesn't help you figure out what that is. So let's try to remember what we learned. We learned directional derivative in chapter 5. So from chapter 5, recall that we learned that df over d vector u is basically equal to gradient of f, dot product vector u. Interesting thing to note is the following. If f map from Rn to R, then what we know is that df over d vector u also map from Rn to R. Reason being df over v vector u is, technically speaking, I know is a directional derivative, but directional derivative is also partial derivative. And we already established that partial derivative does have closure. Therefore, allow us to repeatedly, allow us to actually generate what we call higher order partial derivative. So directional derivative actually follow the same concept. So therefore, meaning that I should be able to now form the the directional derivative of the directional derivative that we figured out here. So how does that work? This is what it means. If you want to do d squared f over d vector u squared, that would mean you basically take the directional derivative in the direction of u of the directional derivative in the direction of u. And we already know that the directional derivative in the direction of u is gradient of f dot product vector u. So to find the directional derivative of this expression, what I basically need to do is do the same thing that we did with directional derivative. So how does directional derivative actually work? Well, I'll show you. If you want to take the directional derivative of f in the direction of u, that basically means you are doing this. And that results in this. Good. So what I'm going to do now is to basically do the exact same thing. But notice that this inside is basically now this right here. So according to this statement, what I should have here would be gradient of what's inside the directional derivative, which is gradient of f dot vector u dot vector u. So that is how we define second order directional derivative in the direction of u. Now, but of course, that doesn't really help because it's just another mathematical expression that's complicated and no idea what to do it for. So how about we make it a little bit more concrete? Definition, or theorems actually. Theorems 6.4.5, which states the following. For a function f that map from R2 to R, let's say if the function f of xy is equal to z, and let's say we define a direction vector, vector u, which is of uv, then we can define the second order directional derivative in the direction of u is equal to u square d square f over dx square plus 2uv df square over dx dy plus v squared d square f over dy square. Sometimes you see this written this way: u square fxx plus 2uv fxy plus v square fyy. So this gives us a way to define the second directional derivative in the direction of u in a function that went from R2 to R. And of course, because of this theorem, we will only mainly focus on function that only map from R2 to R. Now, show you why this is true. Okay, show you the proof. So the proof actually pretty straightforward. So imagine that you have function f that map from xy into z. Then you will realize that gradient of f would simply just equal to df over dx, df over dy. So therefore, if you define df over d vector u, that would just become df over dx, df over dy, dot product uv. And therefore, df over d vector u would form this expression, u df dx plus v df dy. So now come the next question. What if I now want to do d square f over du, d vector u square? Well, then that just equal to d over d vector u of df over d vector u. So that will be just d vector u of this statement, u df dx plus v df dy. And according to what we know, what we need would be the gradient of this thing dot product uv. So how do I find the gradient of this thing? Well, actually pretty simple. The gradient of this thing would actually just simply equal to d over dx of this expression and d over dy of this expression. So basically just taking the partial derivative of that with respect to x and y separately, and that form my gradient. And so what happens when you take the partial derivative with respect to x of the first expression? Well, that just becomes u d square f over dx square plus v d square f over dx dy. When I apply d over df to the second expression, that just becomes u d square f over dy dx, which I'm going to assume is the same as dx dy, plus v d square f over dy square. Yes, if you think about it literally, what you just do is put the d with the d in front of the f, that become d squared, and you have dx and dx on the bottom, so become dx squared. And then same thing for the second term, put a d in front of the df, therefore become d squared f, and you have a dx and dy, so become dx dy. And then dot product with uv. So when I dot product this, that will become u squared d squared f over dx squared plus uv d squared f over dx dy plus uv d squared f over dx dy plus v squared d squared f over dy squared. And so therefore come down to this expression, which is exactly what the theorems say. That complete the proof. Unfortunately, I didn't have time to actually show you an example on how to use this expression, so I guess we'll have to wait until tomorrow's video. Alright, that's it for today. Talk to you guys soon, okay? Bye-bye.